We thank you so much for coming today. My name is William Leatherland. We're here today to talk about EV versus ICE pollution. That's the main thing that we're going to be discussing today. Within that, we want to understand what does CO2 equivalent mean, because we need to make sure, once again, just like we did in our last webinar, we want to make sure we're always talking about things. We're comparing apples to apples, making sure we're looking at the same things, making sure that we're comparing one thing to another with a common scale. So we'll be using CO2 equivalent in order to be able to do that. Part of that will mean that we'll actually need to be able to discuss what a CO2 equivalent it is, and we'll get into that. So this webinar will be about 30 minutes long with question and answer to follow. You can ask questions in the chat and I'll try to answer them in a moment, or I'll save them to the end depending on if it looks like I'll be able to answer that question as we continue to go through. Now we'll be doing these conversations about once a month. I'm trying to do them once again here at Global MRV. We're trying to do them once a month on emission related subjects throughout the globe, from vehicle development and research to electrical production to testing and validation. And really, I want to hear from you. I want to find out what it is that you'd like to look at. I want to hear what it is that you'd like to learn about as it relates to emissions. We have a lot of expertise and knowledge here, and there's some things that we're still learning, so we can learn this stuff together. So during the webinar, if you think of something that would be relevant that you'd like to even just like kind of debate or discuss, bring it up and go ahead and send it to me in the chat. If there's any sidelines of interest that you think of, go ahead and bring them up. Now, one thing you might be asking is, what is Global MRV? Now, Global MRV is a leading provider of portable emission measurement systems. And we're based in Cheektowaga, New York. Now, portable emission measurement, you might hear it abbreviated as PEMS. Been abbreviated that for a while. So we provide PEMS and other data capture solutions. We're based in Cheektowaga, New York. We serve businesses, original equipment manufacturers, research facilities in the transportation, automotive, and engineering sectors. Our PEMS are really, really reliable, accurate, and cost-effective, and they're used for on-road acquisition and emission testing analytics. We deliver cutting-edge technology and comprehensive data management solutions. So we're not just going to collect the data for you, we're going to help you manage that data. We're going to help you analyze that data. And Global MRV has helped clients improve vehicle performance, ensure compliance, and enhance sustainability efforts for years. The commitment to excellence makes us one of the most trusted partners in emissions monitoring and environmental impact reduction. Now, the next question you might have is, who am I? Who am I that's actually speaking? So my name's William Leatherland, and you can call me Earl. That's my middle name. I've worked at Global MRV for 15 years. I was trained in Six Sigma practices while employed with General Electric, and that becomes very useful in being able to analyze data and really get to where it is that we want to go to be able to reduce emissions. I've worked in engine emissions quantification and research and development, overall vehicle performance and health for all of those 15 years. And that includes all types of transportation, from handheld power equipment to trains and trucks, to research and development of all types of vehicles and emission assessment research for companies. And that's part of what we'll be discussing today, the emissions assessment research and how it works with trying to find out, do you need to move to EV, or can we continue to make improvements with ICE to be able to utilize those? Or maybe you're a company that's actually producing ICE type vehicles or ICE type equipment. We can work with you to help reduce those emissions, and you'll see that the difference between EV and ICE vehicles really isn't that large. And so as we can continue to improve ICE to make sure, because they're going to stick around, ICE vehicles are going to stick around. We want to continue to be able to improve those, make them better, because they are going to exist for decades to come. Now, we want to break this down in a way that we've probably never really seen it broken down before, and that's breaking it down from cradle to grave when we're talking about emissions when it comes from an EV versus when it comes from internal combustion engine. Now, the general comparison, you can see it here. If you look at this graph, usually this is what we're talking about. We're talking about that 74%. That 74% that comes out of the tailpipe, and the 0% that comes out of the tailpipe or the non-tailpipe of the electric vehicle. So that's usually where the comparison is, that you would say the EV is 74% cleaner than the ICE vehicle. Well, one thing that we need to also discuss is, as you can see, the manufacturing pieces in blue for the the percentage of overall, and this is what this represents, overall CO2 equivalents, we'll get into that in a second, the overall CO2 equivalent that's produced by an EV versus the overall CO2 equivalent that's produced by the ICE vehicle. 9% of that comes from manufacturing and fuel production in the ICE vehicle, and then 35% and 65% respectively for the EV. And we'll discuss what that is. But as we're going through it, we're going to look at mining and extraction. That's actually getting the materials that we need, to be able to produce the vehicles. Then the manufacturing, actually taking all those minerals and everything, slapping them together, processing them in a way that actually we can actually make a physical vehicle. The fueling is a little bit different, and we're talking about obtaining the fuel. How is that fuel created? Because everything needs fuel. The EV needs electricity. That's its fuel. The ICE vehicle needs gasoline or diesel. That's its fuel. Then the operation, when the vehicle is actually in the hands of the operator and being utilized. When it's in the hands of the consumer and actually being utilized, what's being produced then? And that's usually where everything's focused down on. I want to be able to expand it and look at, once again, cradle to grave, how EV and ICE might match up. And then finally, retirement. Once again, something that we don't usually talk about, or it's usually talked about as everything's just going into a landfill, and that's not exactly the case either. So we need to look at the actual retirement and scrapping of these vehicles. But to start, we need to be able to get something, a similar basis that we're working on. So what we're going to be working on, that similar basis, we're going to build up what is a CO2 equivalent. And we're going to start that by looking at gases that are greenhouse gases that have a global warming potential. So here we have a list of gases, probably the most prevalent ones that are in our atmosphere: water vapor, carbon dioxide, methane, nitrous oxide, and fluorinated gases. And included here sulfur, hexafluoride, nitrogen trifluoride, and hydrofluorocarbons. If you don't know what those are, that's all right. We'll get a brief description of those, but we just want to find out what each one of their global warming potentials, because that's where it really comes to be important, what each one of these actually put out into the atmosphere. So for greenhouse gases, the global warming potential of water is basically zero. And the reason I gave it a 0.0001 is because I wanted to be able to use it in actual equations so that we can have a visualization of how much water vapor actually affects the global warming. Because when we're talking about global warming potential, we're talking about how each one of these vapors actually traps the gas in, magnifies it, and heats up the earth. So we see water vapor, very small magnification, 0.001. Carbon dioxide, that's where we set the standard at 1. This is where we get our carbon dioxide equivalent. Carbon dioxide equivalent molecule, you could say, only magnifies the intensity of the sun by 1 time, whereas methane multiplies it by 27 to 30 times, or the nitrous oxide, 273 times, and then you get into our fluorinated gases, which have a huge amount of magnification. Their global warming potential is as high as 22,800. You see each one of those listed there: 22,000, 17,000, 1,500. Now, why is it that we don't talk about those? They're much bigger, because they have much less influence, because they have much higher influence if they were at a greater percentage in the overall atmosphere. So their magnification, we're going to multiply their magnification, or their global warming potential, times their actual percentage in the atmosphere. So you see here, this is just a graphical representation. You can see that water vapor doesn't exist for its global warming potential. Then we see carbon dioxide. Once again, it would be a 1 right here, so you don't really see that either. Methane, you start to see nitrous oxide, then you see hydrofluorocarbons, all the way up to sulfur hexafluoride. Now, for actual percentages in the atmosphere, that's what we're going to look at here. Water vapor is anywhere from about 2 to 5% in the atmosphere at any time in any part of the world, and that changes very quickly. The reason we don't talk about water vapor as influencing global warming is because that water vapor only lasts in the air for a maximum, from what I understand, about 2 weeks. So it's in the atmosphere, it magnifies for a certain period of time, but then it falls back down to earth through snow or rain. So it's not staying there magnifying constantly. Whereas carbon dioxide remains in the atmosphere for quite a while. I can't say exactly the number of years, but it produces itself and stays in there for quite a much greater amount of time. But its existence or its quantity in the atmosphere is at 0.04%. Methane is a little bit smaller at 0.0018%. Nitrous oxide even smaller. And then you see the fluorinated gas is even smaller still. But to be able to find out how they influence with their small percentage, we're going to multiply them by that previous number that we had. We're going to multiply them by their actual global warming potential. First, we'll look at a graph and you'll see here is the GHG, the greenhouse gas atmospheric percentages. You're looking once again about 4% for water vapor, and then everything else kind of disappears. But once again, remember, since water vapor doesn't exist in our atmosphere for as long, it doesn't have the same magnifying effect for a long period of time. So when we multiply water vapor by its 0.0001% for its global warming potential, you see it's non-existent. When we multiply that one global warming potential times its 0.04% in the atmosphere for carbon dioxide, you see it. And this is just a visualization. This just gives you a visualization of each one of some of their influence. So you see carbon dioxide comes out as the winner, whereas methane, nitrous oxide are a little bit farther behind, but they are existent. And then you see how the ones that have huge global warming potential, they're smaller. There's not as much of those in the atmosphere. Like sulfur hexafluoride, from what I understand, and nitrogen trifluoride are used in electrical production in order to contain the way electricity is produced, to help electricity production and to reduce overheating. I think that's where it's contained in a lot of electrical equipment. Also, I think nitrogen trifluoride is used in the production of a lot of electrical equipment. But that gives you the reason why we compare everything to a carbon dioxide equivalent, because we want to know how much would this influence if it was carbon dioxide and we have a standard that we can compare it to. I hope that gives you a general idea of how we create a carbon dioxide equivalent and why we use it to measure everything so we have a standard scale. Now, getting back to that general comparison, it's no longer going to be a general comparison. We're going to get a little bit more specific. We're actually going to get into the mining and extraction, the manufacturing, the fueling, the operation, and then the retirement. So we're going to start with mining and extraction for the electric vehicle. Now, mining and extraction for the electric vehicle is mostly based on the battery that's created. It takes about 15 tons of CO2 equivalent to create 1 ton of lithium. That means all the mining process and distribution process, in order to get that 1 ton of lithium out, it produces about 15 tons of CO2 equivalent. So that's just to get 1 ton of lithium. Now, you notice I got ton, T-O-N-N-E, because another thing you need to do when you're going through, you want to make sure you're comparing apples to apples. You don't want to use a short ton because that's a little bit less than 1,000 kilograms. You don't want to use a long ton because that's a little bit more than 1,000 kilograms. 1 ton gets us at a good, scalable 1,000 kilograms, and that's what we're using. So to make 1 ton of lithium, we're producing about 15 tons of CO2 equivalent. 1 ton is equal to 1,000 kilograms. So for one battery, it takes 8 kilograms, you see right here, of lithium to make 1 lithium ion battery for an EV. So we divide that 8 kilograms by 1,000, we get 0.008. It should be 0.008, not 0.0008. So forgive me for that. You can see I got it correct here. So we multiply that 0.008 factor, multiply it by the 15,000 kilograms of CO2 equivalent, because 15 tons would be 15,000 kilograms. And to produce 1 battery, to get the lithium for 1 battery, 8 kilograms, it would be about 120 kilograms of CO2 equivalent. Now we can do the same thing for cobalt and nickel, and we could also do it for manganese, but I couldn't find a good number for manganese, so I didn't want to just throw a number in there. These are some of the most common elements that are used. So for cobalt, you need 12.5 kilograms. You need about 12.5 kilograms of cobalt in every battery, and that would produce about 125 kilograms of CO2 equivalent. For nickel, you need about 17.5 kilograms, and that would produce about 525 kilograms of CO2 equivalent. Now, for the mining and extraction of ice, we're going to say that's essentially zero. Now you might say, wait a second, what about, why did you even put these oil rigs here, or these, these dredging platforms here, if you're not going to count that in? We are going to count that in, but we're going to count that in fueling, obtaining the fuel for the vehicle. Right now, we're just talking about extracting the minerals made to build the vehicle. So we're actually building the vehicle. So it's basically zero when it comes to the ice vehicle, because, and I'm not saying it's zero altogether, but if you had one-to-one comparison of the EV and the ice, they're basically going to wash each other out because they all need similar amounts of rubber, similar amounts of plastic, similar amounts of aluminum. Though aluminum could be considered because about 30% of the vehicles are made of 30% of each vehicle is made of aluminum. But with the EV, that might be slightly higher because that's usually what the lithium-ion battery is encased in. They use other materials at times, but usually the lithium-ion battery is encased in aluminum. So we're basically going to say it's zero, because what you would have to put in one, you're going to have to put in the other. So we're going to wash those out for the sake of this comparison. Now, so far, here's what we have when it comes to the mining and extraction. Lithium, nickel, and cobalt. We've got it all written down here. 125, 525, 125. Nothing so far for the ice because it doesn't have that lithium-ion battery being created. Now, when we move on to the manufacturing part, so we're looking at the manufacturing of an electric vehicle. The comparison that I wanted to make here was making sure that I was talking about, basically a one-to-one comparison. So I wanted to find a vehicle that could go about 450 to 500 miles, but that it was harder to find that with the electric vehicles. I found the Model Y Tesla that goes about 330. So we'll, up factor that. You'll see how we multiply that out. We'll up factor that to be able to make 500 a 500-mile trip. But in that Model Tesla Y battery, Model Tesla Y vehicle, it needs a 100 kilowatt battery. That's what you'd usually find. And that can result in emissions of approximately 7,300 kilograms of CO2 equivalent. That's how much to manufacture the entire vehicle. It's going to be a little bit more for the EV because, once again, manufacturing the lithium-ion battery is going to cost more CO2 equivalent when we get down and actually look at it. So 7,300 kilograms of CO2 equivalent to manufacture an electric vehicle. Now, when we get to the gasoline vehicle, there's not that battery component, but we do have, in order to manufacture it, we still have to put a good amount of work into it. So you're still going to have 5,600 kilograms of CO2 equivalent that are produced in making a gasoline vehicle. Now that includes all the emissions. We're talking about from production of materials like steel, aluminum, and plastics, as well as the energy for all the manufacturing process. That's all included in this. We're looking at 5,600. Now, it's the same amount of stuff that would have been in the manufacturing EV, but once again, the EV is about 1,700 CO2 equivalents more because it has to also produce the lithium-ion battery. So, once we go through on each one of these, at this point, mining and extraction and manufacturing, you see each one of those are lined up. We don't have the totals. We'll total those at the end. But you can see that we have still, the EV is a little bit higher at this point. Now you might look and say, oh my goodness, this graph is horrible. Why would you ever put a graph like this up? I'd be thrown out of every boardroom in the world for putting this graph up. But the reason is I wanted to show you the kilograms of CO2 equivalent per kilowatt hour and how it ranges. It makes a difference. The amount of CO2 equivalent per kilowatt hour is going to make a huge difference in how that electricity is produced. Is it produced by coal? Is it produced by nuclear? Is it produced by solar? Is it produced by wind? It's going to make a huge difference. The examples I'd like to point out, if you see here, you've got the District of Columbia, which is much higher than the rest. It comes out at between 2 and 3 kilograms of CO2 equivalent, or I'm sorry, it might come out between 3 and 4, and we'll see the numbers. I've got them written down on the next page. In fact, we can go down and look at that. So it's 0.456 to 3.614 pounds. And we'll translate that over to kilograms. And that's what these orange bars are. That's the number of kilograms of CO2 equivalent per kilowatt hour. So you see here, the District of Columbia is much higher. And the reason they're much higher is because they can't get solar power and wind power located right there close within the District of Columbia. Whereas Vermont has plenty of space and they don't have a big state. They can use just solar and just wind, and they can also use hydroelectric power. Because what I found out is that based on transmitting power from solar and wind, there's a whole lot more loss that is made by transmitting it over a far distance. So you'd rather use solar and wind very close to where it is that you need to utilize it. So solar and wind should be on site, whereas District of Columbia has to import all theirs. So they're getting it from different types of sources. They're getting it from natural gas, from nuclear, from coal. They're getting it from a whole lot of different sources, which means their CO2 equivalents, their kilograms of CO2 equivalent per kilowatt hour is going to be higher. And I wanted to just kind of get a basis on, looking around the world, because it makes a difference on where your power is produced. In the United States, we've got natural gas running at 44%, nuclear at 19%, coal at 16%, and then you see all the other renewables, wind, solar, and alternate renewables that would include things like hydroelectric power. They come out to be about, 21%. So if you look at the world, I thought it would be, much more renewables throughout the world, and it is a higher percentage, but coal is the number one way of producing electricity throughout the world. So coal at 36%, nuclear at 10%, natural gas at 23%, with your renewables, solar and wind coming in at about 31%. So a little bit higher for the renewables throughout the world. Now I wanted to base this off of numbers that I could come close to verifying. I went through a lot of different websites, a lot of government websites and university websites and university papers trying to get appropriate numbers that I could use. And this is based on the United States. So as we looked in that previous graph, the average came out to 0.456 to 3.614 pounds of CO2 equivalent per kilowatt hour. And that comes out with an average of 0.93 kilograms per kilowatt hour. Once again, I wanted to look at a difference between small EVs, mid EVs, and large EVs. And we really had to look at large EVs because they're the only ones who could travel, excuse me, they're the only ones that could travel 100 kilowatts or could travel the distance that we're looking. 100 kilowatts and a Model Y can get you about 330 miles. So using that comparable vehicle, 100 kilowatt hour battery times 0.93 kilograms of CO2 equivalent per kilowatt means every time you charge that battery to produce that electricity, this is the fueling, the fuel that we're creating, the electricity that's being produced, was going to produce 93 kilograms of CO2 equivalent per charge. So for an average of 330 miles, we want to base it off a 500-mile trip. So that would mean you would need to fill up or recharge that battery 1.52 times to be able to get to 500-mile trip. And that would give you, for a 500-mile trip, 153.8 kilograms of CO2 equivalent. That's how much to produce the fuel, the electricity that's needed for an electric vehicle to go 500 miles. Now, for fueling, this is where we didn't include it in the extraction and mining, because we're talking about actually creating the fuel that is needed to be able to put into a vehicle to go 150,000 miles. Refining 1 gallon of gasoline comes out to an average about 3.28 kilograms of CO2 equivalent per gallon. That's just to create that 1 gallon of gasoline. So for 150,000 mile trips, or 150,000 miles at 25 miles per gallon, which is about the average of an ICE vehicle these days, we would need 6,000 gallons of gasoline. 6,000, which means to produce all the gasoline for the operational lifetime of that vehicle, it would produce 19,680 kilograms of CO2 equivalent. So here's our total at this point: mining and extraction, manufacturing, and adding our fueling. This is just fuel production. This isn't actually burning the fuel. We're actually going to get that next. That's going to be included in operation. Now, for the operation of the electric vehicle, the CO2 equivalent, this is usually where it's completely based off for the EV. It's essentially zero because there is no tailpipe for the electric vehicle, no tailpipe at all. So there's really nothing produced while the vehicle is running. We get into, tire production of the, what type of pollutants are coming off of, the tires, but you'd have to do that with ICE vehicle as well. Now there are some lubricants still needed, but they're less than the ICE vehicle, so I didn't add them into the numbers. So we're essentially saying the operation of the electric vehicle is zero when it comes to CO2 equivalents. Now ICE, this is where usually the numbers start to grow for ICE, and they absolutely do grow. So we not only want to look at the fuel, but we also want to look at the lubricants and the fluids that are needed. And I just took a couple here. So the number of oil changes per life cycle, we're saying, let's say 2 oil changes per year. I hope you're changing your oil a couple of times a year. It's very good for the car. And that helps with the longevity of your car, and also reduce the amount of emissions because it's working much more efficiently. You don't have to burn as much gasoline in order to work that efficiently or to get that amount of miles. So 2 oil changes per year at 10 quarts of oil per year, saying about 5 quarts per change. Over 12 years at 150,000 miles, we're looking at 120 kilograms of CO2 equivalent for all that oil in that vehicle. Now the transmission fluid, 2 transmission fluid changes in a lifetime. I was wondering if you guys could put it in the chat. How many times do you actually change your transmission fluid? I know some people do, some people don't. I don't usually change my transmission fluid for the entire life of my car, but now that I see this, I will probably start changing it at least, I think might be recommended every 60 to 100. Oh yeah, I see in the chat here. So so every 60,000 to 100, 60,000 to 100,000 miles. That's where they're recommended. So you probably need to change your transmission fluid a couple of times. So 10 quarts of transmission fluid 3 times, or because we'll talk about that first transmission flush as well. We're looking at 30 kilograms of CO2 equivalent for that transmission fluid. So we got 120 plus 30. And then here's the one that's always discussed: the operation of the internal combustion engine. To burn 1 gallon of gasoline, now we're not talking about producing it now. We've added those numbers in. It was about 19,600. To burn 1 gallon of gasoline, it's about 8 kilograms of CO2 equivalent per gallon. And for a 25 mile per gallon vehicle for 150,000 miles, we're looking at about 48,000 grams of CO2 equivalent. So that's where the number really jumps up for us. The number gets a lot bigger because 48,000 kilograms of CO2 equivalent really jumps it up. And if we look, our totals now with mining and extraction, manufacturing, fuel production, and then fuel usage is what we're talking about. And then, so you see for the ICE, this is where it really starts to catch up with the EV, because you have fuel usage at 48,000, oil at 120, and transmission fluid at 30 kilograms of CO2 equivalent. It really starts to add up. Now, the last thing that we want to discuss is retirement, because that's not usually something that's discussed much. We don't talk about it much. So now we want to look at, retirement of vehicles. The CO2 emissions, retirement and scrapping is not usually discussed much. Now, for both vehicles, you're going to have a similar type of scrapping process, but when it comes to the EV, you've got to scrap that battery or recycle that battery. Most of the time, this part of the discussion just devolves into, once again, someone saying, oh, they just take the battery and they just dump it in the ground and it just poisons the earth. But they have good recycling programs that they're working in. When it comes to recycling that battery, it's anywhere from 1.8 to 2.5 kilograms of CO2 equivalent. That's per kilogram of battery. So we're not talking about kilowatt hours anymore. we're talking about the actual size of the battery. And for the CO2 equivalents, the average would be about 2.15 CO2 equivalents per kilogram of battery. And for the Model Y, that can travel about 330 miles per charge. And that battery weight for that vehicle is 530 kilograms. So we multiply that 530 times 2.15, and we get 1,159 kilograms of CO2 equivalent. Now for the scrapping of the ICV, it basically comes out to zero. Once again, the reason I'm saying it's zero, I know it's not zero, but I'm just kind of taking off the pieces that would be for the EV and the ICE. They would be equal, other than the EV having the lithium ion battery having to be recycled and scrapped. So that's where the bigger number comes in for EV. We've already, excuse me, factored in. We've already factored in oil and transmission fluid already and accounted for it in the operation phase. So this is where we have right now: mining and extraction, manufacturing, fuel production and fuel usage, operation, oil and transmission fluid, and the retirement scrap. I put 1,139 here. It should have been 59. That's really not going to throw off our number by maybe 0.1%. So when we get to our final comparison, you'll see that for the EV, it's 55,710 kilograms of CO2 equivalent. For the ICEV, 73,430 kilograms of CO2 equivalent. Now, most of the time, the discussion comes back that a EV will basically come to be relatively zero and will eliminate its carbon footprint or match its carbon footprint as compared to an ICE vehicle after 1 year of operation. That's not what I quite find here. What I find is that, yes, the EV is about 24.1% less emissions than the ICE over a lifetime cycle of 150,000 miles. The EV overtakes the ICE vehicle and becomes zero at about 113,000 miles. So 113,801 miles, that's the approximation of what I got. The EV overtakes the ICE when it comes to years in about 9.48 years. Now, I'm sure you can find numbers that maybe reduce this or increase it some, but this is not including numbers related to the environmental impact of solar panels or wind turbines or their use of sulfur hexafluoride or nitrogen trifluoride. That's a discussion for another day on how the electricity is produced and what's the actual greenness of that electricity. That's a discussion for a whole nother day. But when it comes to the actual comparison of EV versus ICE, these are the numbers that I found. And this is important. And the reason that we talk about it here, and if anybody wants questions about where I got this information, these are all the different websites I got them from. I'll be happy to share any of them with you. You can freeze the video right here or take a picture of the video right here so that you can see which ones I utilize, but I'm happy to send them out to any one of you in the chat or anybody who views this video later to show you where I got these numbers from. I tried to be really balanced. I tried to get things from the government, from petroleum companies, from electric companies, from the Sierra Club, from universities like MIT. I tried to get a whole bunch of different views on it, and then take averages, and you'll be able to go through and maybe get similar numbers. I'm sure the numbers you'll find some things a little bit different. But why do we discuss this with Global MRV? Why is it important for Global MRV? Well, it's because. So why is this important for Global MRV? Why would we discuss it? Well, we're trying our best to help you reduce emissions. We're trying to help you measure the emissions that you have. So at Global MRV, we specialize in providing cutting-edge solutions to measure, reduce, and verify emissions, helping universities, OEMs, research and development entities, and government regulators achieve their sustainability goals. Our comprehensive suite of services includes advanced monitoring technologies, data analytics, and expert consulting, ensuring accurate and reliable emissions data. For universities, we offer tailored programs that integrate seamlessly into academic research, enabling precise tracking of campus emissions and fostering a culture of sustainability among students and staff. OEMs benefit from our industry-specific solutions that enhance product life cycle assessments, optimizing manufacturing processes, and ensure compliance with stringent environmental standards. Our collaboration with research and development entities drives innovation, providing the tools and insights needed to develop and test new technologies aimed at reducing emissions and improving environmental performance. For government regulators, Global MRV delivers robust verification and report frameworks that transfer and support policy development, enforcement, and transparency, ensuring that emissions reduction targets are met and maintained. So we'd like you to join us here at Global MRV. We're more than happy to help for you to be able to assess what your needs are, what your transportation needs are, and how you can advance even while still using the ICE vehicles. ICE vehicles will be here, I think, forever. I don't think they're ever going away. And because of that, we need to be able to improve them constantly and regularly. And we can, with our tools and our analysis capabilities, we can help you do that and determine where you can switch to EVs and where you need to have ICE vehicles in your fleets. So that's why we discuss it here at Global MRV, and that's why we bring up this topic today.